Hello everyone. So in this second video, we're going to talk about how to compute those two trigonometric series. So they look the same. We just change cosine in sine in one or the other. So the first one is the sum of cosine nx divided by n, and the second is the sum of sine nx divided by n. How can we compute those series? I will first denote by I of x the first sum, the sum of cosine, and j of x the sum of sine. For x, strictly between 0 and 2 pi, just so that, especially the first one, it has to be defined. Okay, the trick here is that if you want to compute them, there is a way to use the Fourier series and the well-known theorems. And the second the other tricks is to use the fact that cosine is the real part of exponential I and x, and sine is the imaginary part. So actually, if you just compute I of x plus I j of x, you end up with the sum of cosine of nx plus I and sine nx divided by n. And it's just the sum for n equal 1 to infinity of 1 over n exponential I n x. Now, the problem is that we have a very annoying term, which is 1 over n. Why is it annoying? Because if there is no 1 over n, of course, the sum does not converge, but it looks like a geometric series. So the trick is to introduce the function f of t. It will be the sum from n equal 1 to infinity of t at the power n divided by n exponential I n x for t between 0 and 1. Why we have to introduce that? It's simply because when we're going to derivate f, well, the n will disappear. And the computation will be legitimate if we take t strictly between 0 and 1. And of course, as you can see, if we can compute f of t, then we just have to compute f of 1, and we just get our two series, initial series. Okay, so let's start. So if t is strictly less than 1, we can compute f prime of t. It will be the sum from n equal 1 to infinity of t at the power n minus 1 exponential I n x. So just so that the two index indices are the same, we have n minus 1 for the first one and n for the second one. I will just write it like this. I just put exponential ix in front of the sum, and then I just set k equal n minus 1, and I have this series. So it's just exponential ix of the geometric series of t exponential ix, okay? And this can be computed because now we have that the modulus of t exponential ix is strictly less than 1. So we get exponential ix divided by 1 minus t ix, exponential ix. And since f of 0 is equal to 0, we can just integrate this function f prime, and we get minus log of 1 minus t exponential ix, where log is the complex logarithm. And in this case, it's well defined. There is no problem. We can define it on a certain domain, but here there is no problem. It works. Okay, so now, as I said before, we have to take t equal 1 to get our initial series. But you see, our computation, it only works for t strictly less than 1. But something that we have to notice is that when t is equal to 1, the series is convergent. Okay, and since our expression is continuous, the thing that we have computed, well, there is a result which is simply called Abel's theorem, one of the Abel's theorem, and which says that in that case we can just take the limit when t goes to 1, and we get that I of x plus I j of x will be indeed f of 1, and in that case minus log of 1 minus exponential ix. Now we have to compute a complex logarithm, and to do that we have to remember that the logarithm of z is going to be the log of modulus of z plus I, the argument of z. And in that case, the argument will be between minus pi and pi, strictly. Okay, so how to compute the modulus of 1 minus exponential ix? Well, there is a well-known trick, which is to factorize by exponential ix over 2. And At the end, we get minus 2i exponential ix divided by 2 sine x over 2. So we easily get the modulus. It's going to be 2 absolute value of sine x divided by 2. And we easily have in the argument, it's simply going to be x minus pi divided by 2. And now we are basically done, because we have that I of x plus I j of x will be minus ln of 2 absolute value of sine x over 2 minus I x minus pi divided by 2. In other words, if x is strictly between 0 and 2 pi, the sum from n equal 1 to infinity of cosine nx divided by n is going to be minus ln of absolute value of 2 sine x over 2. And the sum from n equal 1 to infinity of sine nx divided by n is going to be pi minus x divided by 2. So the two series look much the same, but actually the result looks very different. So it's pretty nice. Thank you for listening.